this clip is about question number 7 on AIME 2011. I think this was the first AIME, not the alternate one. So let me just write it down, AIME 1. Okay. And by far, according to my experience, I consider this like one of the hardest 7. I consider it, like by my experience, because I don't like this type of questions, first off. But that being said, still, we need to solve this type of problems as we go over the past exams. And as we go over the past exams, this brought some kind of a glitch between the intuition, and at the same time, it also brought some problems on expressions, I guess. So according to the expressions, we have m to the power of x naught, and of course x naught supposed to be non-negative integers, so let's try to write out all those non-negative integers nicely. And I think this is worth going over as a clip instead of just like written expressions or just like a solution written in notes. The reason why that's true is because if you just see this like in motion, I guess, the solution in motion, you will get the gist better than just something that is written on notes or some prep books or on the internet. So that being said, I'll just keep going on, and I want you to go over all these materials in detail, and of course just try to understand the fullest explanation as much as possible. So m times x to the power of 1 and m times x to the power of 2 and dot plus m times x to the power of 2011. Okay, so right now we have m, which is a positive integer, so m supposed to be positive integers, and x naught is supposed to be some non-negative integers. But if I divide this by m to the power of x naught, because supposedly it's not going to be 0, right? It's not, none of them is going to be 0, so I can divide it out by m to the power of x naught. So we finally have x1 minus x naught, and m times x2 minus x naught, and dot plus m to the power of x 2011 minus x naught. Okay? So it is quite clear that if I have, the x1 minus x naught supposed to be some negative numbers, and x2 minus x naught supposed to be negative integers, because we need to have some fractions to come up with the sum of 1. Alright, so, what's going on here? Well, I think we can rewrite this, relabel this as m times y to the power of 1, and m times y to the power of 2, and dot plus m times y, m to the power of y sub 2011, and there we go. We have this expression. Now, I had this glitch as I go over this on the offline class for the 특강, so to speak. When I went over this, on the 주말반, on the weekend class, I had this glitch that all the students in the class, they are of course like AIME qualifiers, and they are, they are pretty good at math. They're really good at math, in fact, really brilliant. And they also noticed the same glitch as I did. It's not the problem. It's not the questions problem. It's just it has nothing to do with it. It's just like our mindset. It's just like working out, but not really properly properly being able to set up equations or expressions. So let's try to see what's going on. Okay. So if y1 and y2 and y to the power 2011 supposedly -1, let's say, and we obviously have 1 over m, right? So it just makes sense that we may have 1 over m plus 1 over m plus dot plus 1 over m plus 1 over m. And supposedly, if we have m number of times of m, then we can solve this type of questions, right? We can solve this type of questions. And that's the first impression that most of you, especially who are solving the questions, most of you will feel that that's true. Well, obviously, that's that's true. However, what if, you can say, you can definitely argue about this point about y2 being -2 or y3 being -3. And by the way, we don't even know whether things are written in like nice order. So we can, assume that y1 and y2 and y 2011 are progressively, getting decreased. So if y1 equals -1, then y2 is at most -1. You know, like we can assume that type of possibilities because we don't know how things are written in order, but again, like the additions are all commutatives. So we can safely assume that, you know, it's getting, you know, smaller and smaller and smaller. We don't know. If necessary, we have to relabel it. Now, the problem is, with this expression, it just feels like we can't actually write things in nicer form. You know, that's a problem. However, you know, like as I thought about this, and one of my students actually gave me this idea as well. You know, he said that what if we start to put 1 over m squared? What are we going to do? Well, I thought about that process as well, and we were assuming that what if we have 1 over m, and we have m minus 1 number of times, and we kind of make the last term as 1 over m squared times m. What if we allow such expressions? Well, that's still 1, okay? This is still 1. But wait a second, if you think about this process, and then I think this is quite clear that we have m minus 1, and you can also argue that we can borrow some other expressions again for that typical expression. Like we can kind of, you know, borrow 1 over m squared times m, of course, like m number of times of 1 over m squared, because that's just supposed to be 1 over m squared. And if we borrow that from the second list, then we still make this possible. So it seems like if you have this expression as well, I think we can change this as well. Like, you know, like we've been kind of analyzing, some kind of expressions. We get 1 over m times m minus 1, plus 1 over m squared times m minus 1, and plus 1 over m cubed m minus 1, plus 1 over m to the power of 4 times m, still borrowing from the last term. We still have 1. So maybe you can change the first term because we want to set up certain expressions related to m and certain number. Okay? So we may actually argue that this is still true. Right? That's still true. Okay, so let's try to look at this carefully and nicely. All right? If you choose one of the terms on the bottom, like if you choose one of the terms on m to the power of y1 and m to the power of y2 and all the way to m to the power of y sub 2011, if you choose one of the terms that are equivalent to 1 over m, and if we slightly, you know, like push it to, you know, in this case to the left side, but on our case, on the bottom case, if we push that term to the right side, I think we'll get 1 over m times m minus 1 equals 1 minus 1 over m. Okay? How many terms do we have? Like, how many terms do we need here? I think we need to have 2010 number of terms. Okay? Let's try to look at the same expressions down here. You know, like you could have seen the same expressions down there. Well, I guess that was exactly the same expression as this one. Right? The same thing as you've seen in this particular setup. So if you go on to the second expression, now we start to see some kind of a weird expressions. We have 1 over m times m minus 1 plus 1 over m squared times m minus 1, which is equivalent to 1 minus 1 over m squared. Does that make sense? Like if you start to look at the second, you know, like the check mark, well, that turns into 1 over m times m minus 1 plus 1 over m squared times m minus 1. And of course, you're pushing this 1 over m cubed times m onto the right side, and we get 1 over 1 minus m squared. Now we have 2010 terms down there as well. We got 2010 terms down here as well. We got 2010 terms in that expression. Now what we notice is that m minus 1 is supposed to occur most of the times. M minus 1 will occur all the times. Just doesn't matter whether we have 1 of m minus 1 or 2 of m minus 1 or 3 of m minus 1. All of those expressions supposedly what? Should be 2010. Right? The number of terms that appear on the left side is supposed to be 2010, not 2011. Now the reason why I had this type of idea, you know, like stuck in my mind is because I thought that I should use 2011 at my best. you know, because this is year 2011. This question was, you know, like brought up in 2011. So I was, in my mindset, I was thinking about, hey, you need to somehow use 2011, but there's not much divisors of 2011 to think of. So I was kind of shocked because as I go along all this process, now we're using 2010 as of a factor. Okay, so we're using 2010 as of a factor. So in the end, all you need to work out is whether, you know, like we have m minus 1 times 1 matched with 2010 and m minus 1 times 2 matched with 2010 and that. We keep looking at all those possible values of m minus 1s, which means that we have a parentheses and an integer multiplied together to come up with 2010. All you need to figure is whether m minus 1 is a factor of 2010 and not, right? So, you know, like it's way better if you see this all in motion, right? I told you that this is going to be way better if you see this in motion. So we're looking for all positive m such that m minus 1 divides 2010. Okay, so I think you need to factorize 2010, right? So if you factorize 2010, well, let's see. Let me erase all of this. We have m minus 1 supposed to divide 2010, and you can see that 2010, it's just the product of 2 and 3 and 5 and 67. So how many factors do you find out there? The factors that you find out there is supposed to be just like 2 times 2 times 2 times 2. There are 16 factors, so to speak. So m minus 1 can be 16 different numbers, so there are 16 values of m. Hence, the solution for our question is supposed to be 16. Okay, you know, like this question was kind of nice because we started off from the basic intuition, but however, you have to look at certain patterns that appear. Now, those patterns, unlike what has been written online, I don't think that's obvious. You know, like I don't think that's obvious. Well, people who solve this type of problems will say, oh, this is obviously, you know, like you can notice that. Well, I don't think that this is obvious. You need some kind of experienced eyes. Now, that being said, you know, like other than just like a short written answers, I think going over this as a, you know, like YouTube clips are going to be better for your understanding. So I hope you enjoyed it. And that's it for this clip.